When we think about scheduling in computer science, it's easy to just see it as a solved problem, something about algorithms and queues that you memorize. But honestly, that's a huge mistake. Today, we're going to look at scheduling theory for what it really is, the science of control.
So, in the world of systems, right, a lot of our constraints are, well, they're kind of flexible. If a server is running low on memory, you can literally just buy more and plug it in. You can expand your capacity.
And hey, same thing with storage. If you run out of disk space, you just attach more. For the most part, our critical resources can be scaled up when we need them.
But there's one resource where that just doesn't work. One thing that is totally, completely inflexible. We can't buy more of it. We can't build more of it. Time is the one truly scarce resource we have.
And that one simple, unchangeable fact is what creates the entire problem we're going to dig into today. Because anytime you have multiple jobs or processes all fighting for that same fixed slice of time, a decision has to be made. And that decision-making process is scheduling.
Okay, so how do we decide who goes first? Let's kick things off with the most obvious, the most intuitive way to do it, and then we're going to watch it just spectacularly fall apart.
And that brings us to first come, first served. Yeah, it's exactly what it sounds like. You get in line and you get helped in the order you showed up. It's simple, it's clean, and you'd think it's perfectly fair.
I mean, think about it. This is how we line up for pretty much everything in real life. It just feels like the definition of fairness, doesn't it? Well, yeah, not so fast.
Okay, so this is where that whole intuitive idea of fairness just completely shatters. Picture this, a single-lane road. A massive, slow-moving truck, that's our big, long-running task, gets there first. And right behind it, 3 super-fast sports cars, our quick little tasks. Now, because of our fair first-come, first-served rule, what happens? Yep, those sports cars are just stuck, fuming. The big truck hogs the entire road, and suddenly the average time it takes for everyone to get where they're going goes through the roof. That, right there, is the convoy effect.
The fact that such a simple, seemingly fair system can fail so badly, well, that really shows us what the real challenge of scheduling is all about. It's not about finding one perfect algorithm. It's about navigating a set of goals that are constantly at war with each other, what we call the impossible trade-off.
See, every single scheduler is trying to juggle these 5 things. We want high throughput, just getting as much work done as possible. We want low latency, so things feel instant. We want fairness, so a background process doesn't get ignored forever. We want predictability, so the system behaves consistently. And of course, we need priority compliance, so that a critical alert isn't stuck waiting behind some routine task.
And here's the absolute fundamental truth of it all. You cannot have all of these at the same time. It's impossible. If you push for maximum throughput, latency for some tasks might become terrible. If you enforce perfect fairness, your overall efficiency might tank. You just can't have it all. You have to choose your compromise.
Okay, so if we can't have everything, what do? How do we actually manage these impossible trade-offs? Well, we engineer our way around them. And the main idea is to trade a little bit of raw brute force efficiency for a whole lot more control.
And the single most powerful tool we have for this is something called preemptive scheduling. Basically, it's the scheduler's power to interrupt a task that's currently running. It can just tap it on the shoulder and say, all right, your turn is up for now, let's give someone else a shot. This one concept is what makes your computer feel fast and responsive even when you have 100 things open at once. So let's really see this in action. On one side, you've got our old friend FCFS, which as we know can lead to those awful convoys. But on the other, we have something like round robin, a classic preemptive scheduler. It gives every single task a tiny little slice of time, and then it just cycles through them. The result? It feels incredibly fair and really responsive. But, and there's always a but, it comes at a cost. All that stopping and starting, saving where one task left off and loading up the next, that's called context switching, and it has real overhead.
And that really brings us to a huge lesson here. Fairness costs something. Engineering a system that feels fair and responsive isn't free. You pay for it with performance. And round robin is just one way to do it. You could try shortest job first, which is great for wait times, but requires you to predict the future. Or you could use a priority scheduler, but then you risk completely starving out the less important tasks.
All right, so we've been deep in the weeds with algorithms and trade-offs, but now let's pull way back and look at the big picture. Why does any of this really truly matter? Because all these technical choices are really about one thing: power. The scheduler is the one who decides who gets to go and who is forced to wait.
And look, this is not some abstract theory that only matters inside your laptop. Scheduling is happening everywhere, all the time. It's in the massive cloud data centers that run our entire digital lives. It's in the database query planners figuring out how to get your data. It's even in physical manufacturing pipelines on a factory floor and in the tiny network packets zipping across the internet. It is everywhere.
And this is what's so critical to understand. When a huge modern system fails today, it's almost never because some single algorithm was flat out wrong. No, it's way more likely that it's a scheduling failure, a total breakdown in how time and resources were allocated. Because as we've seen, scheduling is an impossibility problem. Designing a scheduler is really about choosing which compromises you're willing to live with.
So, let's wrap this all up with the single most important idea from this whole explainer. Think of it like this: algorithms. Well, algorithms decide what can be done. They define the universe of what's possible. But scheduling decides what actually happens. It takes that world of possibilities and brings it down to reality, deciding who gets to go now, in what order, and, this is the most important part, who is forced to sit on the sidelines and wait.
So the ultimate lesson is this. If you really want to understand where the control is, where the real decision-making authority in any complex system truly resides, don't just look at the clever algorithms. Look at the scheduler. Because in any real system, that is where the power lives.